All right, so we're just going to go over various techniques. So section 5, by the way, is just more of the same. It's problems from everything we've done so far. Okie doke. First thing we got to do, oh, we did do one like this the other day. All right, that's okay. Let's do it again. It's up there. Long division. X squared minus 1. I like to put a 0x in there. Goes into 5x cubed plus 3x squared plus no x minus 4.
Why do we have to use long division?
Because the degree of the top is larger than the degree of the bottom. So what you can't do partial fractions unless the degree of the top is smaller than the bottom. You can't even be the same. Okay, so I can do an example like that too in a moment. Tyler?
Can you use synthetic division?
You cannot do synthetic division. So pretty much the only time you can do synthetic division is if you have something like whatever in the numerator, that doesn't matter. But the denominator's got to be like x minus some number.
Can't you split it up though, because it's technically x minus 1, x plus 1?
And then do a division by 1, take the result and do a division by the other. So you have to do 2 sets of synthetic division.
Easier than long division.
I don't know.
No, it's not.
Maybe. Yeah, so if it factors into linear factors, then you could do synthetic division into parts. That should work too. All right, so here I need to ask myself, what do I multiply by x squared to get 5x cubed? And on a good day, the answer is 5x. And then multiply gives me 5x cubed plus no x squared is minus 5x. And then I like to subtract by adding the opposite. So I just go through and change signs. And I don't really care about 0. So this column gets eliminated. 3x plus no x squared is 3x squared, and 0 plus 5 is 5x. And then bring down the minus 4. I subtracted by changing signs and adding. All right, what do I multiply to get 3x squared?
3
Plus 3. And let's see, that's going to give me 3x squared plus no x is minus 3, right? Mm-hmm. And subtract by adding opposites. And that annihilates a column. 5 plus 0, x is 5x, and negative 4 plus 3 is negative 1. So that's my remainder there. So then we've rewritten this integral to be the following. We're still going to get my message, huh? Try again. It's now, so this is the quotient, the result, like the whole number part of the answer. So I get a 5x plus 3 plus the remainder is 5x minus 1 over the denominator. I'm going to write that in factor form, x minus 1 times x plus 1. Yes. So that's the first step. And then we have to do partial fractions on that remaining fraction. And notice now it's a proper rational fraction. The degree of the top is smaller than the degree of the bottom. And that has to be the case. All right, let me try pinging Ms. Miller one more time, see if we can get her live. Sam, did you tell her
did you already
message her through my open math? Messages. New message. Nope, wrong button. There's the message. Ms. Miller. Okay, hopefully that goes through to her. All right, so let's do partial fractions on that second part. So we know what A and B are, right? They are what, 5 and 3? Is that what we got so far?
Yes.
Yeah, so now we have to find C and D. So, new page. 5x minus 1. All right. So we need to rewrite 5x minus 1 over x minus 1 times x plus 1 as something over x minus 1 plus something over x plus 1. So then we multiply through by the lowest common denominator, a bunch of stuff cancels. So I think the next step should look like this. 5x minus 1 equals a times x plus 1 plus b times x minus 1. Yes, sir?
Where'd you get the 5x minus 1? Because that just be long division of
That was the remainder of my long division here. If I didn't make a mistake. So if we don't match, one of us has a mistake.
plus 3, if you multiply it by minus 1, it's
That was what we thought for the initial division, and there's remainder.
Yeah, so in this last step here, I take 3 times negative 1. That gives me negative 3, but I have to subtract negative 3, which means I'm adding 3 to get that remainder. So it should be 5x minus 1 then. So I can come back to that later if you're stuck on that. All right, what do we do next?
Find good values.
Find
of x.
convenient values of x, right? I like to plug in 0, but that's not as convenient as, say, 1 and negative 1. So I'm going to go for x equals 1 first. I plug in a 1 for x, that gives me 5 minus 1 is 4. On the other side, I get 2a, and b has volunteered itself to go away. And so a must be
2. How convenient.
And then other convenient value is negative 1. And so let's see, negative 1 times 5 is negative 5. Minus 1 is negative 6. And a becomes 0, so I have equals b times negative 2. And so dividing out the negative 2, I get b equals 3. All right, so 2 goes with the a minus 1. Okay, so here's my new integral. My new integral is 5x plus 3 plus 2 over x minus 1 plus 3 over x plus 1. You think I get everything in the right spot?
Yes.
I think I did.
So the 3 would be your D, right?
The 3 is what I have for, yeah, so this, according to the way the homework problem listed it, I believe that's A, that's B, that's C, and that's D, but I gotta go double check. Because they might have C and D backwards, depending on how they wrote those two factors.
So when I put 3 in for my D, it's like, no, you need like 3 ln x minus 1 plus.
Really?
So, yeah.
Let's see. So let's see, what did I say? A was 5 and B was 3, C was the 2, that went over the x minus 1, and D, I believe, was 3. All right, and let's get an integrand here. Actually, I can just, oh, it says show answer, look at that. Yeah. Oh, it's in review mode.
Yeah, you could just show the second to
Okay.
last one.
5, 3, 2, 3.
It didn't like that.
Oh, so you just had some weird special thing. I'll look back at yours later
Okay.
and we can check it out. All right, let's come up with an antiderivative. Is there going to be more than one answer to these problems? Yeah, because there's usually more than one way to do it, slightly different steps. But hopefully the computer is set to take multiple different kinds of answers, and usually it is. Antiderivative for 5x.
5 halves x squared.
Plus 3x. All right, antiderivative for 1 over x minus 1.
ln of x.
ln,
or
we
ln
have the
absolute
2
value
hanging
of x.
out. Yeah, so we'll have 2 natural log, absolute value, x minus 1 plus 3 ln absolute value of x plus 1, and then plus c, which I may or may not have to write. Could I clean this stuff up if I wanted to?
Yes.
Yeah, LNs have lots of magic properties. I'm not gonna worry about it though. This is an excellent stopping point. So how close did I get? 5 halves x squared plus 3x plus 2 times, they skipped the absolute value.
Oh, shame.
Should have put it in there. And then x plus 1. So
I
let's
think
see.
it still takes it though. I don't think it sees it as that detriment.
All right, let's try another. Does anyone else have a homework problem?
16.
16 is a cutie, huh?
Uh-huh.
Ooh, I love volumes. I'm so glad we got one of these. All right, let's do it.
It took me a lot longer than I
Roll this up a touch. Screenshot.
Okay, skip that.
You have to differentiate the why.
All right. There will definitely be something like this on the take-home exam.
Oh, so there is a take-home exam.
There is going to be a take-home exam. Yeah.
I have to actually pay attention. I have to pay attention, Gary.
What's up with that dragon?
It's motion.
Oh, is that like Mulan's dragon?
Yeah.
Okay.
Gary. I feel like
It's been a long time since I've seen Mulan.
Fabula.
Okay, so volume generated by revolving the area bounded by 4 different functions. So we definitely have to graph this to figure out what area, so we have the boundaries. That's like the hardest part of these problems. All right, so interesting. Let's see, what do we need? I prefer GeoGebra these days. GeoGebra graphing. And let's see if I can type this correctly. Pull it over here so I can see it. All right, so I'm going to call it f of x, and it is 1 over x cubed plus 9x squared plus 18x. Ooh, that's a gorgeous graph. All right, so then we're bounded by x equals 2, x equals 5, and y equals 0, which is the x-axis, but I want to graph it anyway. I'll throw a color on there. All right, so I just need to zoom in. We'll really zoom in there. Let's switch tools. Okay, so here's my top function, well, side graph, bottom function. So I want this region right here. And so we would have to determine those intersections here, which GeoGebra gives me. What's up?
Is this finding the volume of the object revolved around the axis?
Yes,
Which axis is it?
it's going to be around the y-axis. Yeah, so I'm getting there. All right, so now I need to sketch this sucker. Okay, so we got a picture on the computer. You should, who do we have online? Ms. Miller, welcome. Always do a hand-drawn sketch too, to the best of your artistic ability. So we have 1, 2, 3, 4, 5, 2. And then we have some vertical scale. I'm not going to worry about that a moment. I have this boundary, I have that boundary, and I have this boundary. And then I have my curve swooping through like that. So it's this region right here. And even though we're not finding the area, it is an excellent idea on your hand-drawn picture to shade that area to remind yourself what region you're playing with. Because you're going to have to decide on disks or shells next. Okay, so we're going to revolve this around the y-axis, so indicate your axis of rotation, right? So this is all stuff I expect to see. And then now it's playtime. So let's see. If I were to do disks, then I have to go perpendicular to the axis, which means I have to change functions. I don't like that.
I tried to do that and it like plugged it into an algebra thing and it just like wouldn't give me anything.
Yeah, and I would also have to solve, because this means I have a dy, which means I have to solve this for x.
Which is a nightmare.
It is a nightmare, William, agreed. So that's something you do on Friday night instead of watching the Avengers. About as much fun. All right, so I think we all convinced ourselves that we should use shells here, because with shells, my function is always on top and y equals 0 is always on the bottom. So I'm going to make a note to myself. I'm using shells. Let's see, shells look like that when I revolve this thing right here. So that's my height. That's my height. And then I need a radius, which is the distance from the axis of rotation to that height thingy I drew it. Okay, so that's r. Okay. Well, let's take a look. Let's see. If I'm doing a shell, then I have a dx, true? So that means my radius seems to be just x in this case. Right? X is the distance from the y-axis to whatever that vertical bar x value is. Okay, so that's cool. And the height seems to be just what? My function, right? What I was calling this guy right here f of x. So my height appears to be just f of x. And then the volume of this skinny little shell right there is the circumference, which is 2 pi r times the height times dx. And then I just need to add up all of them, which is the integral. So my integral is going to be 2 times pi. I just determined r is x, and h is that wonderful rational function x cubed plus 9x squared plus 18x. And then dx is the thickness of that shell there. Okay, so reminder, all the things I had to write down to get started, I had to find the region that's going to get rotated, so I know my bounds of integration. I had to decide whether I was using disks or shells based on the axis of rotation. Okay, so I want to label that axis, I want to draw in a line for a disk or a line for a shell to kind of figure that out. Once I'm working on that, I tell myself, is this a dx or a dy? That's important too. How often do you choose like the wrong value, like x or y? Does anyone ever do that? You pick the y values to integrate from, but you're really doing the x? I mess that up all the time. So other reminders I do to myself, since I'm using a dx, I'm also going to write x equals by the integral to remind myself to pick the right numbers. So x equals 2 to x equals 5. So those are all the things I need to do to get this set up right. If I skip any of those steps, I'm likely to make a mistake. So that was the hard part, I think. The next hard part is coming up with an antiderivative, which is only partially hard here. Questions on the setup? Yes?
Yeah, it's like which method are we going to use to?
Oh, we'll get to that next. Yeah. So we got to set it up. Now we got to clean it up and decide what integration technique to use. So, new page. So I'm going to pull the 2 pi out. That's a constant. I'm going from 2 to 5. That's okay. And that leaves me an x over. And I'm going to try and factor that thing. I can pull an x out of it, which is very convenient. Leaving, let's see what, x squared, 9x, and then 18. X squared plus 9x. Was it all pluses? Mm-hmm. Okay. Yeah. Like everything? Mm-hmm. 2 pi r h. Yeah. Okay, there's everything. So that's kind of cool. And x divides out. A number divided by itself is 1. The bottom, let's see, 8 is 3 times 6. So that factors as x plus 3 times x plus 6. So one technique I can apply is partial fractions, because this is the partial fraction section. Does anybody remember the other technique I showed a while back? I could complete the square on the denominator. That's another option here. We'll get a slightly different answer. We'll try that next for fun, because that's something you could do in 3.5. I might have a problem with that. All right, partial fractions. We take a break from the integral for a second, and we say, all right, we believe we can write 1 over x plus 3 times x plus 6 as some number a over x plus 3 plus some number b over x plus 6. multiply through by the common denominator. 1 equals a times x plus 6 plus b times x plus 3. We get some cancellation. Good idea to pause there, make sure we cancel the right stuff. If this were on a test, I would fill in the step I just skipped. The step I just skipped was I just thought about multiplying through by the common denominator, but I didn't write it down. On a test, you definitely want to write that down and not do that in your head. Right, Kyler? You write everything down. And then confirm to ourselves, yup, cancel, cancel. What does it mean to cancel?
Back to 1, divide by.
Number divided by itself is 1, right? That's what it means by cancel, right? So number divided by itself is 1, multiplying by 1 is boring. All right, yeah, I think I did that right. Convenient number time. -6 it is, so x equals -6. That leads to 1 equals, this term zeroes out, the a term. The b term, -6 plus 3. On a test, I would actually write b -6 plus 3. Make sure I'm not messing anything up. When you put on paper, the more your brain is free to double check it. So what do we get? -3b. So b must be -1/3. Repeat, x equals what? -3. So 1 equals a times -3 plus 6. And let's see, b is definitely zeroed out, right? Yep. Not a bad idea to write that down under pressure. -3 plus 6, 3. So a is +1/3. All right, we got our a and our b. Time to rewrite the whole thing. 2 pi on the outside. And let's switch colors. Integral from 2 to 5 of, let's see, a was +1/3.
Yes.
That was my order. Yeah, always make sure you line them up right. Okay, so a goes over the x plus 3. So 1/3 over x plus 3. And then we have plus -1/3 over x plus 6 dx.
Can we write that the same as 1/3 times 1 over?
You could have written it, yes, correct, as 1/3
Fraction, then.
times 1 over x plus 3. That would
Same
work
thing.
also. Same thing. Got it. All right. The 1/3 is actually constant in both of them. So I could just pull it out. So I could say out front, I have a 2 pi over 3, right? Because 1/3 is the same as dividing by 3, multiplying by 1/3, dividing by 3. And then my antiderivative, that's now just a 1 in the top. So I just need the natural log, absolute value of x plus 3. And then here I would have a -1 because I pulled out the 1/3. So minus natural log, absolute value of x plus 6. And evaluate it from 2 to 5. Let's keep going, just for fun. 2 pi over 3 times, plug in 5 first. Remember, top number goes first. So that would be the natural log of 8 minus the natural log of 11 minus parentheses, to be careful, plug in 2, natural log of 5, because they don't need absolute value anymore, well, minus the natural log of 2 is 8. Could we clean this up into a nicer answer?
Yes.
Sure, just for fun. If you subtract two the same logarithm, that's like dividing their arguments. So these two could become the natural log of 8/11 minus, do the same thing there, the natural log of 5/8. And then I can do that one more time because I have another subtraction. So that would be the natural log of, let's see, that would be 8/11 divided by 5/8. So that would be, instead of dividing by 5/8, I could multiply by 8/5. I was hoping the 8's canceled. Bummer, they didn't. But we can simplify the answer down dramatically. So the final answer could be 2 pi over 3 times the natural log of 64/55. Eek. The hardest part, I think, was the setup. That was even harder, I thought, than using partial fractions.
I took a page.
That was like a full page on paper, right? Yeah, most of these problems are. Mental note, don't assign so many problems to next year's crew. Sorry, guys.
Maybe they deserve to suffer.
I already get some pizza and pie. How about Thursday? I'll bring pizza and pie.
You were gonna do that anyway because
Oh,
it
right.
is
Because
a
it's
national
It
holiday.
is a national holiday. All right,
Or, you could just cut down the number of problems we have to do.
sure. How about I make one of the next sections optional?
Really?
Is
Right.
it?
Yeah,
Yes.
Legit?
Yeah.
Seriously?
yeah.
But we're
So
still gonna need to
great.
know it though, right?
Thank
If
you,
I make it
Sarah.
I like
Yeah. Okay, so we'll do another problem in just a sec. Let's take a look.
If we do it, do we get optional points?
No, yeah, you get extra credit. We just went over this.
It's because it's not extra credit.
Okay, so numerical integration, which is beautiful, and improper integrals, which is also beautiful. Okay, which one should I make optional? Flip a coin, maybe?
Numerical integration
Which
is
one's
a
harder?
trapezoid.
Numerical integration is harder?
Then let's skip that one.
It's a trapezoid.
Which one will help
All
us
right.
better next term?
So,
There's only, why don't you just roll a d4 and then
All right.
subtract 1?
roll that for me. Okay, Dylan got a 4. So if my dice is even, then we ditch numerical integration. If my
Okay.
dice comes out odd, then we ditch improper integrals.
Well, how
Okay.
about if it's a 4, then we just ditch both of them?
Yeah. It's a 1 in 16.
Come on, Gary, it's a pretty low probability you're gonna roll a 4.
1/6, that's like almost 17%.
That's pretty low.
I don't know if I can do that.
Yes, you can.
No, wait.
How about if it comes out of 4, I can't do it, but if it doesn't come out of 4, then I'm okay with that.
What?
That's like my grandfather used to say to me, okay, well, flip a coin, heads I win, tails you lose. All right, here we go.
Oh.
It is odd. What does that mean?
Giving improper intervals.
Nah, we'll skip numerical integration.
So it's simply wrong.
Okay.
All right, so let me modify this and put a giant optional out front.
Which one has more questions?
I can fix that. Let me save this. Let's change the color to.
3-7 is 14 questions.
Is that the one we're not?
How much is
That's the
3/6?
one we're doing.
Okay, that's good.
Okay, so that one's now optional.
3/6 is 14.
3/6 is 14. But they're, so this is basically all Riemann sums.
Oh, thank goodness.
And not only Riemann sums, but Riemann sums, we focused on the right endpoint. Here they focus on midpoint, trapezoids, and what's called Simpson's rule, which is basically trying to fit a parabola to the top of a couple. Instead of a straight line segment, you try to fit a parabola to the top of a few.
Yeah.
Oh, and then you take the
Which is
integral
quite
of the
beautiful.
parabola.
Well, it ends up with this remarkable formula that's actually kind of simple, that you can program a computer to do. So for example, on one of your take-home problems, I asked you to do a surface area first around the y-axis, then around the x-axis. and one of them was kind of hard, the other one was really, really hard. It was so hard that I couldn't write a formula to plug into the computer for the exact answer. I was forced to have to use something like Simpson's rule to come up with the answer. Right? So,
Is any of that used in Calc 3?
no, none of this is in Calc 3. So, all right, yeah, so we'll do numerical integration next. No, I lied. We'll do improper integrals next. Tomorrow, numerical integration now optional, which means if you do it, it'll count as extra credit. Once to figure out how that works.
Is that still on the same due date then? Because if we're moving
Okay.
7 forward.
Let's do some
Also,
housekeeping
is
while
that-
we worry about it.
is
No,
that-
stop, wait, no, I'm gonna do one question at a time. Please be quiet for a second. Hold that thought, Sam, no offense. All right, so 3-6, I'm now gonna put on Sunday night. Improper integrals, I'm gonna move to Friday.
Can we have more time for 3-5?
Thank you.
Whoa, look at that.
That doesn't mean wait till Thursday to do them. Today is Tuesday. How about this? I'm gonna put it here for now, and then maybe move it tomorrow.
I feel
Okay.
like that's.
That's fair. We did
Because
this
otherwise,
Thursday.
if you're a human being like me, you'll be like, I got till Thursday. And then all of a sudden Thursday's here. Okay, let's do another
You
problem.
read my mind.
I haven't.
Yes, sir. Okay,
Number 2.
all right, 3-5, number 2. Ruh-roh.
Ruh-roh, Raggy.
Oh, nice. Okay.
No,
Let's do
no.
it. Oh, I got this one. Screenshot.
I actually opened the textbook for once. Are you proud of me?
Textbook.
I read the textbook for the.
What textbook? What's the textbook for this class?
I know, right? Mom and I read it all the time, but she has to tell me the math homework.
Yeah, first time somebody asks me a question I'm not familiar with, I'm like, can I see your textbook, please? Or I Google it. You know, Google's amazing these days.
Okay.
I didn't have Google when I was in college. It's not fair. I didn't have GeoGebra, I didn't have Desmos, I didn't have Google
Yikes.
calculator. I just had this big old book I had to look stuff up in.
How much does that book cost you?
Hang on, what was that, William?
Did you have the office back stuff?
No, there was the internet. Let's see, how old am I? I'm 49. The internet was just being developed and it wasn't really publicly available for most people when I was in college.
So you had to go to the library.
Did you know it's the 30th anniversary of the internet right around now?
Yeah.
That's it?
Oh, no, the World Wide Web, I'm sorry. The internet has been around since like the 70s. But the World Wide Web wasn't around until, when would that be? The late 80s.
So how much did that book of answers cost you?
I didn't buy one. It was in the library.
Oh, that's good.
Or the math department had one. Yeah, so we would all go to the math lounge and go, hey, can you get that book, please?
You could open these.
All right, let's do this. We're running out of time.
Trying to find the.
Okay,
That's
do
right.
substitution first because we got to get out all those e to the x type objects.
Gross.
All right, so let's see. I think I'm going to let u equal e to the x. Yeah, and here's why I'm making that decision. I'm looking at the denominator here, and I'm thinking if that was the square root of like u squared minus 36, then it looks familiar to me, like something we did from trig substitution, or a sine, cosine, or arc sine, arc cosine, arc, one of those arc functions. So that means I need a square. Well, there's the 2 and the e to the 2x. That's going to be my square. Because e to the 2x is e to the x squared. True?
Yeah.
Power to power, you multiply the powers. Okay. So based on that, I'm thinking I would like u to be e to the x. Now, we might say, hey, let's let u be e to the 2x minus 36. But that could be a problem deciphering the top, is what the mess I would find myself in, I think. All right, so then du would be what?
E to the x
E to the
dx.
x. And hey, I can factor an e to the x out of the numerator to make that happen.
Mm.
Okay. All right, so I'm going to rewrite that numerator before I do my substitution. So my claim is that I'm going to pull an e to the x out of the numerator, which is like, factoring is like dividing, right? So if we take e to the 3x and we divide by e to the x, what do we get?
E to the
E to the 2x. Yeah. E to the 2x divided by e to the x would be
E to the
e to the x, I'm gonna get a 5 e to the x, and then 6 e to the x, I factor out e to the x, it's just a 6. So, and then I'm just gonna put a times over here. I factored out an e to the x is still chilling over there, and down here, I'm doing that e to the 2x as e to the x squared. And I'm gonna call that a 6 squared for now, because we're gonna look that up in the table in a moment. We can do it without the table, but we'll look it up in the table. All right, now I'm ready to substitute. So I need a page to make that happen. Copy, right.
Oh goodness.
What happened?
In the back, there's 130.
There's a lot of them, yeah. So finding the right one in the table can be sometimes tricky.
Just Control F.
Yeah, Control F can sometimes help. All right, so based on my u substitution, that right there is my du. So I now have e to the, and remember u is e to the x. So I think this guy right there is a u squared plus 5u plus 6 over the square root of u squared minus 6 squared. Du. That's where I'm at now. From there, we're going to have to, I doubt there's something that looks like that in the table. Seriously doubt. But you never know. We're probably going to have to break this down in terms of the numerator
Gary, open the
and write it as
text
3
book.
fractions. I'm getting there, I'm getting there. All right,
Check
so,
Equation 82.
Is that top factor?
Equation number.
maybe. That's a good question. Let's see, where am I going?
You have to open
Where's
up
the book?
text.
Open the book.
You have to.
I'm just ticking away. Constants, integral tables. Which one did you think? Number what?
Number 82, but it's missing.
Uh,
It's missing.
It's got an x squared, yeah, okay.
it's close.
And, well, so let's see, 82 is close, 81 is kind of close.
We have to combine them.
Yeah, so here's what we're gonna do.
Oh,
In order to do this, we're gonna have to break this up into 3 integrals
Oh, okay, that's not that
based
bad.
on those sums.
so
So I'm gonna have to write a little tinier to fit this. So we're gonna have to view this as the integral of u squared over the square root.
Do we get this table of integrals on the test?
I hope so.
So we don't have to add that ourselves.
Plus, right, the integral of 5u over the square root of u squared minus 6 squared u plus the integral of 6 over the square root of u squared minus 6 squared du.
We got a hot seat.
Ooh, all right, thank you, Dylan. Guys, this is a u. Yeah, so it was a formula number 81, was this one right here?
80.
Or 82. So that was number 82 in the book. This one over here is number 81 in the table of integrals in the book. This one, is it in there?
80 for the cat.
Okay, so we have a u squared minus an a squared. It's not that, not that, not that, not that, not that. That's that last part. Not that, not that, not that. It ain't in there. Okay, what are we gonna do?
It's a trig substitution.
We could do a trig substitution, maybe. Let's see, so we have, so this one wasn't in the table. So what, 5u, I'll pull the 5 out. U over the square root of u squared minus 6 squared. Okay, I got another idea. Let's do a v substitution, because we've used u. So here, I'm gonna let v equal u squared. Then dv would be what?
Oh, you.
2u.
It would be 2u, du. I'm just missing the 2. So I could go in here, a couple ways to deal with it, right? I could put a 2 there, divide by 2 there.
Yes.
Then rewriting this in terms of v's, I get 5 over 2 integral of, oh, even better. Actually, let's make this u squared minus 6 squared.
Oh, yeah.
It's just a constant.
because the derivative is still that.
Uh-huh.
So now I have, this right here is my dv. That's over v. And then I have 1 over the square root of v, which I would rewrite again. Red 5/2 integral of v to the negative 1/2. So its antiderivative is going to be, what, add 1 to that, which gives me 1/2, and then we would have to divide by 1/2, which means multiply by 2. Oh, that's fortunate. So 5/2 times 2v to the 1/2. And we know that v is really this. So I get this is equal to 5 times the square root of u squared minus 6 squared. And so then based on the table and that, we put it all back together. And yeah, we got to plug back in our u, which was the e to the x. All right, let's take a quick look at the table. Do we have 1 more minute?
No,
Oh,
we're
we're
out
out
of
of time. All right, so I will email everybody a message reminding them about the changes in the schedule for this week. And Sarah emailed me my deadline to get those practice tests, those take-home tests done. Thank you, Ms. Arden, for your help for the group.